Hello students, welcome to EPG Pathshala and I am Reema Gupta from University of Delhi. Today we are going to discuss about the module Electrical and Magnetic Properties Part 5th and this is from the paper Ceramics. So students, let us see what we are going to learn in this module. So we will be discussing basically the three types of polarizability. So the first is electronic polarizability, second ionic polarizability and third dipolar polarizability. So before moving further, let us discuss what is polarizability. So polarizability is the ability to perform instantaneous dipoles. It is a property of matter and the polarizabilities determine the dynamic response of a bound system to external fields and provides insight into a molecule's internal structure. In a solid, polarizability is defined as a dipole moment per unit volume of a crystal cell. The relationship between polarizability and the factors of electron density, atomic radii, and molecular orientations are there. So, the greater the number of electrons, the less control the nuclear charge has on charge distribution, and therefore the increased polarizability of the atom. However, the greater the distance of electrons from nuclear charge, the less control the nuclear charge has on the charge distribution, and thus the increased polarizability of the atom. Whereas if we talk about molecular orientation, so the molecular orientation with respect to an electric field can affect the polarizability except for molecules that are tetrahedral, octahedral or isohedral, that is oriented independent, or we can say orientation independent. So these factor is more important for unsaturated molecules that contain areas of electron dense regions such as 2,4-hexadiene. So we can see that the greatest polarizability in these molecules is achieved when the electric field is applied parallel to the molecules rather than perpendicular to the molecules. So students, we will be discussing the types of polarizability, that is electronic, ionic and dipole, one by one. So the first is microscopic response. Earlier we saw that polarization in a system with n dipoles per unit volume can be expressed as P is equal to n into mu, where mu is the permeability. Now, P is also given as N into Q into delta. Here N is the number of dipoles per unit volume. This gives the susceptibility Xi, which is equal to epsilon r minus 1, which is equal to P upon epsilon naught E, which in turn is equal to NQ del divided by epsilon naught E. Hence, greater is the value of delta, greater is the Xi, and hence larger in epsilon. That is, more polarizable a medium is and more is its dielectric constant. Further, the polarizability of an ion or atom in a dipole of type where I is defined by alpha I is equal to mu I divided by E local, which is equal to Pi divided by Ni into E local. So where E local is the local electric field experienced by an atom or ion or molecule, which can be different than the applied field. However, the magnified of local field can be modified quite significantly the polarization of surrounding medium. As a result, P can be expressed as P is equal to Ni alpha I E local. Note that this equation relates macroscopic parameter P to the microscopic parameter capital N, alpha and E local. As a result, in general, susceptibility is xi is equal to epsilon r minus 1, which is equal to n alpha by epsilon naught, where alpha is the sum of all types of polarizabilities due to different mechanism like alpha electronic, alpha ionic, alpha dipolar and alpha interface. Now let us analyze the polarizability. Here we discuss the simple analytical solution for determining the polarizability and polarization for each of the above polarization mechanism which we have talked about in the previous slides, that is electronic, ionic, dipolar or interface. We analyze the polarization mechanism and the analysis will shed some light on the dependence of polarizability on the material parameters as well as any external parameters. So the first is electronic polarizability. So to achieve this, let us imagine an atom as a perfect sphere having plus Ze charge at the center of the nucleus and an equivalent minus Ze charge of electrons around it. So it is resemblance of the figure which is shown on the left hand side. Here capital R is the radius of the atom. So you can see the schematic for the electronic polarization. So under the application of electric field, that is E, the force on the charges is given as F is equal to Ze into capital E. As a result, positive and negative charges experience forces in different directions and their center move away from each other by a distance small d, which is also shown in the figure. However, d has to be finite because this force is balanced by Coulomb force of attraction between opposite charges, which can be calculated by simple electrostatics and is given by F is equal to Q of nucleus into Q of electrons inside, which are separated by the distance d divided by 4 pi epsilon naught d square. So the term becomes Ze into Ze multiplied by 4 by 3 pi d cube by 4 by 3 pi r cube divided by 4 pi epsilon naught d square. So the net term come out to be F2 is equal to Z square E square d upon 4 pi epsilon naught r cube. Now equating the two forces which we have discussed in the previous slide, which gives the equilibrium separation and the distance is d naught. So the distance d naught by equating the two forces comes out to be 4 pi epsilon naught r cube E divided by Ze. The induced dipole moment, that is mu, would be mu is equal to Ze d naught or mu is equal to 4 pi epsilon naught r cube E. So if the dipole density was n, the polarization can also be calculated. And it is given as P is equal to 4 pi epsilon naught n r cube E. So the equation for the electronic susceptibility and electronic polarizability becomes the electronic susceptibility is 4 pi n r cube and electronic polarizability is 4 pi epsilon naught r cube. So this is very important result as it allows us to work out the electronic contribution to the dielectric constant. This also shows the linear relationship between polarization and electronic field for electronic polarization mechanism. Another point to note is that the polarizability of atoms with S and P atoms like alkaline and rare earth is more than the transition elements. That is, D atoms due to higher shielding of nucleus by electrons in D atoms. So the equations which we have discussed shows that the larger the atom is, larger is the polarization. Moreover, anion are more polarizable than cations as electron is an anion, outer shells are more loosely bound. So students, you can see the values of atomic polarizability of some atoms are shown in this table. So let us take one example. Assume a typical value of dipole density N and atomic radius capital R for a material made up of atoms with spherical symmetry of orbitals. So students, it is given that the value of dipole density and atomic radius. So let us assume that the dipole density is equal to 4 into 10 to the power 19 per centimeter cube, whereas the atomic radius r is given as 7 into 10 to the power minus 19 centimeters. So students, you all can calculate the value of susceptibility. So the value of susceptibility, that is Xi E, comes out to be 7 into 10 to the power minus 4, which is very small value, and the relative dielectric constant epsilon r does not increase by much. So what it says that the electronic polarization effect is generally very weak and contributes very little to the overall polarization. Having said that, it must be borne in mind that some materials like silicon, that is Si, which are covalently bonded and the orbitals do not have spherical symmetry, and as a result, the dielectric constant can be higher, and for example, it is silicon which has about of 12. So for electronic polarization, that is epsilon r, is also equal to n square, and hence if one knows the refractive index, his work as a check for the values calculated will be very easy. Ionic polarizability. So this figure shows that in an ionic solid, in the absence of external electric field, all the dipoles formed by each Na plus and Cl minus pair with an equilibrium separation distance as d naught cancel each other due to crystal symmetry, and hence the net dipole moment is equal to 0. Remember, in these solids, no dipole rotation is allowed. However, when a finite field, that is E, is applied, the force experienced by the ions leads them to move away from their equilibrium position as shown in this figure, so giving rise to unequal dipole moments in different directions, and as a result, the material will have net dipole moment. So as you now see that the distance between the ions decreases by d in one direction and increases by d in opposite direction. Now we calculate the magnitude of d. The force F1, which increased the distance between the ions of charge, can be expressed as F1 is QE. However, there is another force which is acting in opposite direction, so which tries to restore the equilibrium between the ions, which is expressed as F2, which is equal to Ki into D. where K is the spring constant of the bond between the ions, assuming ionic dipoles behave like springs. So the spring constant can be expressed in terms of elastic modulus, that is capital Y, and it is Ki is equal to Y into D naught. So at equilibrium, F1 and F2 are equal, and so combining the above equations we get that D is equal to QE upon YD naught. Now let us discuss about the dipole moment and polarization. So the induced extra dipole moment, that is mu, is given as Q into D, where Q is the charge and D is the separational distance. So mu is equal to Q square E upon YD naught. So in this case, we have substituted the value of D, which we have calculated in the previous slide. So mu comes out to be alpha I into E. Here alpha I corresponds to ionic polarizability, which is equal to alpha I is equal to Q square upon YD naught. So from where this expression has come? Let's see. So we know that the polarization P can be written as N into mu. So N into mu is equal to N into the value of mu, that is Q square E upon YD naught. So the polarization now becomes NQ square E upon YD naught, where N is the dipole density per unit volume. So students, please note that here we considered electric field E parallel to the main crystallographic axis. If this is not the case, one needs to take the component of dipole moment in the direction of field before adding them together. This is a very rough guide to calculate the ionic polarizability and can be more complex in the cases of many ionic solids, especially when ions do not have similar charges. For example, in calcium fluoride, that is CaF2, a material used for making lenses for lithography machines, the dielectric constant is approximately equal to n square. So this enables the lens to made of the dimensions of about 0.1 micrometer. So students, you can see the following table showing the values of dielectric constant of some materials where ionic polarizability contributes in addition to electronic polarization. Now comes dipolar polarizability, or we can call as orientation polarization. So in case of dipolar polarization, we have materials where dipoles are present independent of each other. That is, they don't interact and they can be rotated freely by an applied field, unlike in case of ionic polarization. So one such example is water, that is H2O molecule. So H2O molecule has a dipole moment, and these dipole moments are free to rotate and can have any rotation with respect to neighboring molecules. So due to ability of molecules to move around randomly, liquid like water have very limited dipole polarization contribution despite having a permanent dipole moment. So a two-dimensional image of water is shown in the slide, which should remain almost similar at any instant. So the arrows depicted in this figure depicts the direction of dipole moment associated with each molecule. So it is quite obvious by looking at the figure that in the absence of applied field, all the moments are randomly distributed, that is huge number for even a small amount of water, say 10 milliliter, and net dipole moment would be 0. Now when we apply an external field, say parallel to the paper along z-axis or x-axis, let we take x-axis as shown in the figure. The dipoles would tend to align with the applied field to lower their electrostatic energy and hence leads to minimum dipole energy. Basically, positive end of dipole would like to join the negative end of the applied field. In reality, tendency of dipoles to orient along into the field direction will be counteracted by random collisions between the molecules, a process driven by the thermal energy, that is kT, at a temperature T. Moreover, the dipole containing molecules move around at all times due to thermal energy and the associated entropy. We call it as a disorder. So basically, we apply external field. There is a competition between field induced order and thermal driven orders. Later, that is, the thermal driven disorder prevails in liquids more than in solids. Hence, a perfect alignment of dipoles would be possible only at very low temperature and possibly in solid crystals. So as a result of intermolecular collisions and thermally induced random movements, the dipole do not completely align themselves along the field unless the field is extremely high. So basically, the configuration of dipoles looks something like the bottom figure shown in this slide. Now, this basically highlights that the orientation of all the dipoles is just a little bit shifted towards the field direction, leading to an average non-zero dipole moment in the direction of applied electric field. You can see this in the figure on the top side of this slide. So thermodynamically speaking, we will minimize the free energy, that is G, which is equal to H minus Ts, where H is the internal energy and S is the entropy. So for this, now we take the following configuration where the charged dipole of an molecule makes an angle theta to the applied electric field. The internal field, or we can say the internal energy, that is U, of a dipole depends on its orientation with respect to applied field. That is, it is a function of theta. U is minimum when the dipole is completely aligned with the field, that is theta is equal to 0 degrees, and maximum when angle is 180 degrees. So the energy U theta of the dipole with dipole moment mu under an applied field E can be written as U del is equal to minus mu E, which comes out to be minus mu E cos theta. So here mu E is the magnitude of mu and magnitude of E. So now what it means in 3D world is that we would have a cone of dipoles having an angle theta around the applied field E, which points along the axis of the cone, which is shown in this figure. So the total internal energy of the whole material would be sum of internal energies of all these cones. Now we need to calculate the number of dipoles at an angle theta. N theta, which can then be multiplied with the energy for that theta and then be integrated between theta ranging from 0 to 180 degree to give us the total internal energy. However, to calculate the free energy, we should also need to calculate the entropy S, which is not very straightforward. So this is where Boltzmann's statistics rescues us, which allows us to work out the minimum of the free energy using the distribution function. So we treat our system to a good approximation as a classical system containing a number of independent entities occupying various energies as determined by their angle with respect to applied field. the distribution of these dipoles at various energies can be expressed by a distribution function in such a manner that it minimizes the free energy of the system. So for a given temperature T, the number of dipoles with energy U can be expressed as Nu as a function of theta is equal to A times exponential minus U by kBt, where A is a constant, kB is a Boltzmann constant, and T is the temperature. Now the above equation, which we have discussed in the previous slide, provides us the number of dipoles in a cone. Now we should calculate the component of dipole moment parallel to the applied field using solid angle, that is d omega, for a unit sphere in a segment between theta and theta plus d theta. So students, you can see on the left hand side, this corresponds to a dipole cone. This implies that the number of dipoles between theta and theta plus d theta is equal to nu theta into d omega. So the total dipole moment is nothing but the sum of components of mu e of dipole moments in the direction of applied field. So mu e becomes n d omega into mu cos theta. The average dipole moment, that is mu e, is calculated by adding up the contribution of all the solid angles. So it is expectation of mu is equal to integration 0 to x n u mu cos theta d omega by integration 0 to x n u d omega. So the incremental solid can be expressed as d omega is 2 pi sine theta d theta. So on solving the further equation, we get expectation of mu is equal to 0 to pi sine theta cos theta exponential mu e cos theta by kbt into d theta divided by integration 0 to pi sine theta exponential mu e cos theta by kbt into d theta. So on solving further, we get that the expectation of mu e is equal to mu square e by 3 kbt, which is also equal to alpha d into E, where alpha d is the dipolar polarizability and is equal to mu square upon 3 kbt. Now on substituting the value of dipolar polarizability, the value of polarization is P is equal to n mu, which is equal to n mu square E by 3 kbt. So the consequences will be, while electronic and ionic polarizabilities are temperature independent, the dipole polarizability is temperature dependent. So this is manifested by macroscopic dependence of polarization and dielectric constant on temperature. So students, let's now summarize what we have learned in this module. So students, we have discussed that there are three types of polarization. One is electronic, ionic and dipolar. So the electronic polarizability increases with the size of the ion. So the bigger the ion is, the higher is the polarizability. Next, we have discussed about the ionic polarizability. We have read that the ionic polarizability is inversely proportional to the elastic modulus, which is related to the bond strength, and hence higher the bond strength is, lower is the ionic polarization. So the next and the third polarizability is dipolar polarizability. So we understood that the dipolar polarizability is inversely related to the temperature, which explains the drop in the polarization of a polar solid upon increasing the temperature. Thank you.